Hello, welcome to part 6 of our video where we continue looking at the Dasming machine learning library. So in the last video we had taken a look at matrix operation, and in this we'll continue looking at some of the other matrix operations that we support as part of the matrix library. Again, I had mentioned each of these libraries are independent DLLs and you can use them in your project outside the machine learning library, and all you have to do is include the exceptions library. Also, I had mentioned the entire matrix operations are split into different files, but they are part of the same class, and we are using the partial class constructor in C# to make that happen. So let's continue looking at some other functions that we have implemented. So here's the transpose. We are doing a parallel operation for transpose. So a transpose operation converts the rows into columns and columns into rows. It's a pretty straightforward operation, just requires some array manipulation. Now, we had taken a look at LU factorization in the last video, and I had mentioned LU factorization is used to solve a system of linear equations. So we also have a function to solve a system of linear equations defined in the form of a matrix. So we take matrix A and matrix B essentially in this form: matrix A times matrix X gives matrix B, and we have to find matrix X here. So we do this computation to the LU factorization using the LUP matrix function that we had taken a look at yesterday. Then finally, once we compute the matrix X, we return that as a return value of the function. Similarly, inverse of a matrix is any say a matrix A, and inverse of matrix A is something that when you multiply A by the inverse of its matrix, it gives the identity matrix. So just to give you an idea, I've opened this site. This is a really good site, by the way. Math is fun, where we look. It gives a lot of definitions of algebra and matrix operations. So I'll use the reference for both Wikipedia and this site and a few other sites, but here they have explained what a inverse of a matrix X. So if A is a matrix, inverse of a matrix always leads to the identity matrix, and we are aware what an identity matrix looks like. It's all ones on diagonals and zero elsewhere. So we have to find this matrix. So again, we can use a system of linear equations here, right? Because I, we know its I is going to be an identity matrix of same size as A, and we already know A, so all we have to find is A inverse, and so A inverse can be a matrix X that we have already implemented in our system of linear equation solver. So here we do some basic conversions, verify the matrix. This is a basic function that checks if the matrix is in the correct form. Now here we also check if matrix 0.len, basically this is checking if it's a square matrix or not, and then we compute the identity matrix. So identity matrix has been implemented as a single function that returns an identity matrix of size n. Again, it returns a square matrix. So once we have this, let's go back to I inverse, then we solve the system of linear equation where the first matrix is matrix A that has been passed as a function argument, and then we pass in the identity matrix and it returns us the new matrix, which is going to be the inverse of this matrix. Now let's take a look at QR decomposition. Now let me go back into a Wikipedia article. So QR decomposition is a split of a matrix A into a product Q and R, which is an orthogonal matrix Q and an upper triangular matrix R. Now why do we need this? This is used to compute eigenvalue and eigenvectors, and eigenvalue and eigenvectors are again very important for machine learning and actually overall matrix operations in general. In fact, the Google's initial search algorithm used to rank pages based on their eigenvalue. Now what is an eigenvalue and eigenvector? So here's a definition from Wikipedia. Essentially what you're looking at, and you multiply any matrix by its eigenvalue, it returns a matrix multiplied by its eigenvector. So actually let's take a look at math is fun definition, which I find it to be a little bit better than the Wikipedia. So I mean, this is a matrix transformation of an image. So if you transform it, you can change the direction using eigenvector. But at its basic form, what an eigenvector and an eigenvalue is, if this is a matrix, you multiply it by an eigenvector, it leads to the same result when its eigenvalue is multiplied to its eigenvector. So eigenvalue and eigenvectors have a lot of uses, and that's why we have implemented it. And it's also used in some part of machine learning. And specifically, like in our case for the machine learning, it's used in when you're doing dimensionality reduction or feature reduction. So for example, one of the common dimensionality reduction algorithm is principal component analysis, and PCA or principal component analysis is heavily leverages eigenvalue and eigenvector. So it's important to have that function. Plus, it's a very important matrix operation, so any matrix library should contain that. So computation of eigenvalue and eigenvectors, there are a few methods here. I'm switching back to the Wikipedia article. So there are some methods that have been given here, but one of the common ways is also doing a QR decomposition. So we have implemented some methods for QR decomposition, and let's take a look at how we do QR decomposition. So there are some methods like the Gram-Schmidt method is there, then householder reflections, and also using Givens rotation. So using these Wikipedia articles, we have implemented the Givens rotation mechanism and the householder method. So if you look in the householder method, again there's a reference to a paper which gives more detailed of how this is done, and also some other papers that have been written, like this is a paper as Arizona State that references how to compute using a householder reflection. Ultimately, it's basically matrix and manipulation, and which we are using a two-dimensional array. So it's going through the operations of changing the values in the 2D array. Now, as you can see, we are also leveraging some of the functions we already have, like multiply and transpose and identity matrix, and then a multiply by scalar. So multiply by scalar is another operation where we just take a value and specify by any scalar value. So let's actually go it this way here to explain what it's doing. So it's taking a matrix and multiplying it simply by a scalar value. And again, this operation can be done in parallel, so we have used a parallel loop to do that. Similarly, for householder, we have also implemented a method using Givens rotation. Now this method is also called as a Hessenberg method, and Givens rotation has its own separate function. So we have broken this up into different functions because Givens rotation can also be used elsewhere in different matrix operations. So this way you have the flexibility of passing in a matrix and doing a Givens rotation of it. So here we take the value of QR and return the value QR because we are taking it as a reference. So as you can see, the function returns nothing, but it's manipulating the values of Q and R. And also we have some verification. So this is a function that checks if the matrix is square, and then it raises an exception. So this is a common pattern, as we have discussed, where if things don't match, we are creating a separate exceptions class and simply raising that exception. This is our design pattern, and again, this is a consistent thing we have been doing, so it's much easier to expand on it when you add new functions. So with that, we have also implemented a determinant of a matrix, and determinant is also a pretty important operation, especially when you're trying to solve a system of linear equations. And determinant is also based on the values of Q and R. Sorry, L and U. It uses the LU factorization here. By the way, one thing on Givens rotation I didn't mention is Givens rotation is also defined as a rotation within a specific plane. It's different than eigenvalue and eigenvector computation. So we have referenced these articles here and used this example here in the Wikipedia to verify that the matrix is working correctly. So all the verification again has been done in our unit test operations. So we have linked an answer here. So if you go to this link, actually let's open this. This has some online computations where we can verify the results. So there's a QR decomposition calculator where you enter any matrix and it gives you a specific result. A lot of ads in that website. Now for givens rotation, we have given multiple data sets. So here's an example that's taken from the Wikipedia article I showed you. It says init data set. So if you go on the implementation of this init data set, this essentially mirrors what we have here. So 650, 514, that's the matrix that we have defined. Going back to the givens rotation test, let's go down to the wiki. Here's the article. We have done some other testing here using a symmetric row as well as also compared values from R. So this was the data taken and we ran it into our system, and here's another one where we compared it from another article. So this way we have multiple levels of testing being done for this function. Again, as I reiterated, with your mathematical functions you have to have a lot of testing because you have to cover multiple cases for a 2 by 2 matrix and a 3 by 3 matrix. Now normally if it works for a 3 by 3 matrix and a 2 by 2, it should work. It scales up pretty well, so you can extrapolate the results that way. But it's always good to have edge cases and results from multiple sources. So this way, if any changes are done, you can run your unit test and you can figure out if you have broken something or not. Alright, with that, this sums up our review of the matrix operations, and from the next video we start taking a look at some of the core machine learning algorithms. Till then, see ya.